So to start today, we're going to talk about the sine function. We'll follow that up with the cosine function. And then we'll eventually go on to modifications of them. But for now, we'll start with the basic sine function. Just f of x equals sine of x. So no other operations, no other modifications or transformations occurring, just the basic sine function. Now, the first thing we have to do is understand what it is we're looking at with the sine function. We need to understand what are the inputs representing, and as with any of the trigonometric functions, they operate on an angle measure, specifically radian measure here. We don't have the option for degrees. We have to use radian measure for the functions. And then there's the output. The output is going to be different depending on which trig function we're looking at. Sine of an angle is a y-coordinate on the unit circle. So if we want to get some points on the graph of the sine function, we're going to use points from the unit circle, points whose angle we can identify and whose y-coordinate we can identify. Now, a lot of the points on the unit circle have some really ugly ordered pairs to them, some really ugly x and y points. So we're going to stick to, at the moment, four positions of the terminal side that are the easiest to work with, regardless of whether you're dealing with sine or cosine. But for now, for sine. So we're going to start with an angle of 0 radians. Excuse me. Zero radians, which puts our terminal side, well, in the initial position. There's no rotation. That ordered pair is 1, 0. What is important out of these is the angle measure, and since this is the sine function, the y-coordinate of the point. These together give us the statement that sine of 0 is 0. And that leads to the first ordered pair that we have for our sine graph. An input value of 0 radians and an output value of 0 for the y-coordinate on the unit circle. Now, the next easiest angle to work with is the 90 degree or pi over 2 radians angle. That puts our point on the circle right up here. We have an angle measure of pi over 2, and this point is 0, 1. So again, our values of interest here are the angle measure pi over 2 and the y-coordinate of the point, which is 1. This gives us sine of pi over 2 is equal to 1, and that becomes the ordered pair on our sine graph, pi over 2, 1. Now, I took the liberty before we began of marking the x-axis with every other tick mark is pi, a distance of pi, and that means that halfway in between is pi over 2. So we now have a point at pi over 2, 1. Now, what's happening in between there, we'll come back to. Let's go on to the next nice angle to work with. Halfway around the circle, an angle of pi radians. And this point on the circle is -1, 0. So again, the x-coordinate, the -1, is not relevant here, but what is relevant is the angle measure and the y-coordinate of the circle. Now I'm going to have to relocate this down here. We have the statement sine of pi is equal to 0, which becomes the ordered pair for the sine function, pi comma 0. Up here on the coordinate grid, we have a new point to mark. So now I want to talk about what's happening in between those points. Sine is the y-coordinate. And as our angles go around the circle, the y-coordinates grow until they hit their biggest value. And then after that, as the angles continue around the circle, those y values shrink again. They go from the tallest down to a shorter y value and then a shorter y value until finally they reach a y value of 0. So what's happening in between these points is the output value of the sine function is getting bigger and bigger until it reaches this maximum point, and then it comes back down. Much like the y values on the circle start at 0, they grow bigger until they reach their peak, and then they come back down. So you can see that the arch that we just drew here is not circular, but it does have the same basic idea that it starts from 0, grows up to 1, and then comes back down. Okay, let's continue around the circle. We have 2 more points, 1 more angle, and then a repeat, really. So the next angle, I hope, is kind of obviously straight down. This is now 1, 2, 3 pi over 2 around the circle. So that's our angle. And the ordered pair here is 0, negative 1. So again, our y-coordinate and our angle are what make our ordered pair for the sine function, because we have the statement sine of 3 pi over 2 is equal to negative 1. And that becomes the point on the sine graph, 3 pi over 2, 3 pi over 2, comma, negative 1. So coming up here on the grid again, that puts a new point down here. Now, we don't want to stop there because there is a whole other quadrant of angles we have yet to go through here, the entire 4th quadrant. So I'm going to take it back up to this starting point and say another angle that is coterminal here is 2 pi. But the ordered pair is the same, 1, 0. So the output value is still 0, but the input value, the angle, is now 2 pi. Now, in between these, what we see is exactly the opposite of what we saw in the upper half of the circle. This time, our y-coordinates are going to grow, but with negative values. They're going to get bigger and bigger until they reach their biggest, negative 1, and then start shrinking back down to 0. So in between, we're going to dip down to this low point and then back up to 2 pi comma 0. Now, the interesting thing about trigonometric functions is because they're based on this circle, and because we can rotate around the circle multiple times, we can extend this pattern because it's going to do the same thing again. The same way that when we hit 2 pi, it repeated the same behavior that it had at an angle of 0. As we go around and grow to pi over 2 again, or at this point, it would be 5 pi over 2, we will again have the same y-coordinate in our ordered pair. And that's kind of the thing is, regardless of whether it's our first time going through this quadrant, or our second time going through this quadrant, or even our third or fourth or fifth time going through this quadrant, every single time, the angles might be bigger, but the pattern of the y-coordinates on the circle is exactly the same. So if we traverse the circle a second time, we should see this same wavelength pattern that we see here repeat again, and it should repeat on the same intervals. That is to say, every time we go 1 tick mark to the right, we should see the next part of the cycle come up. So if we go 1 tick mark to the right from 2 pi, we should repeat what we saw in the first section, that is, going up to a y value of 1. And then from there, again, 1 tick mark to the right, back down to an output value of 0. 1 tick mark to the right, down to an output value of -1, and then 1 tick mark to the right, back up to 0. This pattern will continue forever and ever and ever for as many times as we can go around the circle, which is infinitely many, or for as many times as we can fit it on our graph paper. The pattern can easily go the other direction because we can rotate through we can have negative rotation of the angles, in which case we're just reversing the pattern. Instead of going up first, we would, in reverse, go down first, and then back up to 0, and then up to 1, and then back to 0, etc. Down to -1, back to 0, up to +1, back to 0. And again, this pattern would continue forever in both directions. Now, there are certain characteristics of the sine function, and later on the cosine function, that are unique to these functions. We've never seen another function that does this. We've been through polynomial functions and rational functions, and we've never seen anything that does this because it repeats its behavior on a fixed interval. The graph is called a wave because, well, it goes up and down like the waves in the water. Anything that behaves based on waves, like light or radio waves or sound waves, are all governed by, the sine function, or perhaps the cosine function, as we'll see shortly. So there are certain characteristics here that we can talk about. The function itself has, let me clear that off some space here. The function itself has certain characteristics. The most obvious, I suppose, or the most basic is what we call the period. The period is the longest interval along the x-axis before the graph starts to repeat itself. So if we allow the graph to do everything it's going to do without repeating its behavior, we can go all the way up to 2 pi. This distance from 0 to 2 pi, this is called the period. Now, different wavelength or different waves have different periods or different lengths of interval upon which they repeat. We'll get to that in a short bit, but the basic sine function has a period of 2 pi. Now, it doesn't matter where in the cycle you start and where you end, as long as you don't repeat any previously done behavior. So I started from 0 to 2 pi, although admittedly that's maybe a little bit tougher to see here. Maybe a better way to do it would be to take, say, a valley and the next valley. So through that we go all the way up and then all the way back down. And maybe that's a little bit easier to lay out, although the values aren't exactly so nice either. But it's the same thing. If we actually sit here and figure out that distance, it is indeed 2 pi. So that's one of the main characteristics of the wave, the most obvious one to talk about, because it does do something that no function we've seen has ever done, and it repeats its behavior. Now, there are 2 other characteristics in particular that we should be aware of that will help us when we're graphing different sine functions. One of these is the midline. The midline is the line about which the wave oscillates. That is to say, there's a central point that it, or a central output value that it keeps returning to, and at times it may rise above it and at times below it, but it keeps coming back to that one, and it's in the middle. It's called the midline because it's literally half the distance between the peak, the highest peak, and the lowest valley. The midline is a horizontal line, and for the basic sine function, it is on the x-axis. So we have the midline, y equals 0. Another characteristic we have here, then, is what's called the amplitude. The amplitude is the maximum distance above the midline or below the midline that the wave reaches. The maximum distance above and below. It should be the same for both because, again, the midline is supposed to be halfway in between the peaks and the valleys. The amplitude is that distance. And for the basic sine function, it is 1. So let's add this to our library of basic functions. We can talk about the domain, which, well, is all real numbers because we can take any size angle around the unit circle, whether it's positive or negative, 0, any angle around the unit circle, and it will connect to a y-coordinate on the unit circle. So no matter what angle measure we choose to put in, there will be a y-coordinate on the unit circle, and that makes the domain all real numbers, negative infinity to infinity. The range, however, is going to be negative 1 to 1 with brackets inclusive. The output value, or the y-coordinates on the unit circle, never exceed negative 1 or positive 1 because it's a circle of radius 1 centered at the origin. So the highest we can go is directly up one space and directly down one space, but we can't go any further than that. We'll hit everything in between as the angle changes, but the highest it ever reaches is a y-coordinate of 1, and the lowest is a y-coordinate of negative 1. Now, other things we've talked about with other functions were the intervals where it's increasing and decreasing, or the positions of its minima or maxima. Well, this function increases and then decreases, and then increases and then decreases, and so on and so forth. To list out every one of those intervals where it's increasing and decreasing is a little ridiculous. It also peaks and valleys an awful lot. In fact, it's going to keep on doing it over and over and over and over again. So to talk about its extrema is likewise a little bit silly because it's got so many of them. So instead, we're going to use these three main characteristics. The period, which is 2 pi, the midline, which is y equals 0, and the amplitude, which is 1. These characteristics will be much more helpful to us than talking about increasing and decreasing or extrema, because they are much more descriptive of what the function does. Now, that's the sine function. The cosine function. Excuse me. The cosine function. Well, I set up a coordinate plane with the x-axis labeled in multiples of pi, or rather multiples of pi over 2. The only real difference between the cosine function and the sine function, at least to start, is what the output values are going to be. The input values are still going to be angles in radians, always in radians, but the output values, and this is where it gets a little bit odd, the output values are x-coordinates on the unit circle. That makes it a little bit weird because the x-coordinate from the circle is going to be the output value from the function, and that's different from the x that we're using in the function f of x equals cosine x. So you have to kind of follow along here, and we'll see how it works. So again, we're going to use our common angles. Zero radians, pi over 2 radians, pi radians, and 3 pi over 2 radians, and then back to 2 pi radians. Now this time, though, we're going to want to use the x-coordinate of each of these points. This point is 1, 0. The x-coordinate is 1. So we have the statement cosine of 0 radians is equal to 1. And that's going to become the ordered pair 0, 1 on our graph of the cosine function. So we do have a difference already. The sine function, recall, started at the origin. Its wave started at the origin. This one seems to start up at 1. Now, as we progress around the circle, the next ordered pair we come to is at an angle of pi over 2 radians, and has the coordinates 0, 1. Again, what we're interested in here is the angle measure and the x-coordinate from the circle. Cosine of pi over 2 is equal to 0. And that gives us the ordered pair for the cosine function, pi over 2, 0. Now, again, it seems a little odd at first to be looking at x-coordinates and then x-coordinates become output values, but that's why also I'm using the phrases angles and x-coordinate, inputs and outputs. I'm trying to avoid some of that confusion there. Next point up is an angle of pi, and the ordered pair is -1, 0. So again, the angle pi and the x-coordinate from the ordered pair, the x-coordinate is -1. So we have the cosine of pi is equal to -1. And that gives us pi, -1. Now, perhaps this isn't really surprising that we're seeing a very similar pattern of our points here that we saw in the sine function. Cosine and sine do produce the same values around the circle, but they do it in a different order. And that's why the waves are going to look just a little bit different. At 3 pi over 2, we have the point 0, -1. So again, 3 pi over 2, and the x-coordinate from our ordered pair there, 0. And that gives us the statement cosine of 3 pi over 2 is equal to 0. For our cosine function, that becomes the ordered pair 3 pi over 2, 0. Now, this jives with what we saw in the sine function. When we dip below the x-axis, we have to then come back up to the x-axis afterward. So, one more point here. We come back to our initial position, except we've gone around now, so we're at 2 pi radian angle measure, but it's got the same ordered pair as before, so we're going to get cosine of 2 pi is equal to 1. So we're going to see a repeat of the x-coordinates of the circle, but we're going to see it for different angle measures. Now this isn't going to look much like a wave at first. In fact, it really just looks like a kind of a fancy V or a fancy U. And that's, again, because we're not seeing the full effect of the graph. Much like with the sine curve, we saw a single arch and valley until we extended the pattern. But the pattern here is, again, that the x-coordinates start out at their biggest positive value, and then the x-coordinates get a little smaller and a little smaller and a little smaller until they hit 0, at which point they flip over to negative and extend out until we hit the biggest negative x value of -1. And then they come back towards 0, and then extend it out through the positives again. And it's going to repeat this pattern every time we go around the circle. So we're going to, as we repeat the circle here, we're going to go from our biggest positive x value, our biggest positive x value back to 0, and then extend to our biggest negative x value back to 0, and then up to our biggest positive x value again, and back to 0, and so on and so forth. It's the same wave pattern. However, instead of starting at the midline and then going high, cosine starts out high. And just like the sine function, it can be reversed. In fact, it's possibly easier to reverse this one because once you're at the high point, the only place to go from there is to go low, back to the midpoint or the midline, down low, back to the midline, up high, back to the midline, down low, back to the midline, up high. Now, the characteristics of the wave are actually virtually the same. The only difference is how they begin their cycle. So I'm just going to kind of lightly draw up here where the sine function was. Sine, in blue, started out at the midline and then went high, and then back to its midline, and then low, and then back to its midline. So the sine function did this. It's just an offset. Cosine and the cosine function and the sine function are both waves. They're just a little bit offset from each other. Now, later on, we will see there is something called a trigonometric identity, which does actually verify that. But the fact of the matter is that we can use either of them, sine or cosine, to define any wave out there. The only difference is how they start out in their cycle. Cosine starts out high, whereas sine starts at its midline and then goes high. But cosine has got the same characteristics. It's got the same domain because we can, again, go take any angle measure we can imagine and then find the x-coordinate on the unit circle that goes with it. It's got the same range as the sine function, -1 to +1, because, again, whether we're talking about up and down or left and right, we can never go more than one space away from the origin, 0. So we can go as far left as -1 and as far right as +1, but no further. The period is the same as with the sine function because it takes a full rotation around the unit circle to do everything that cosine is going to do. Additional rotations just repeat the same behavior. It's even got the same midline, y = 0, and the same amplitude, 1. Again, the only difference between them is where in their cycle they start. So that's the sine and the cosine function, the basics of them. Coming up, we're going to talk about how to modify these. I know radios are a little bit of an outdated technology nowadays, but if you look at the radio in your car, not the Sirius XM radio, but if you look at the actual radio and the different stations, FM or AM, FM means frequency modulation. Frequency is related to period. Frequency talks about how often the wave cycles through its well, how often it cycles in a fixed amount of time. The larger the period, the fewer times it will cycle. The shorter the period, the more times it will cycle. The period, another name for it is wavelength. If you ever take physics and talk about waves, they use the phrase wavelength. Here we use the word period, but it's the same thing. Wavelength and frequency have a distinct relationship. We can adjust the amplitude as well. That's what AM is, amplitude modulation. Perhaps a more commonplace of the word amplitude is if you've been to a concert or if you play in a band or something, the amps, the speakers. And to be honest, when you turn up the volume, really all you're doing is increasing the amplitude of the wave. So we can adjust all of these things. Midline serves as position, I guess you could say. Whether the wave is being sent out on the left side of the stage at a concert or being sent out on the right side of the stage. So the position, the central position of it, and that the wave is emitted at. But any of these things can be altered through transformations. So before we get into how to create different waves, we're going to do a bit of a review of transformations to start out the next video.